Now I will show you a few questions solved by using the idea of integration. So let's say we have question number 1 here, case 1. So the idea is we have a constant tank as shown in the figure here. So let's say we have a circular cross-sectional area tank like this. So and then at the bottom of this tank, it has a small hole. So the diameter is 0.05 and the CD is 0.6. So the CD here means the discharge coefficient. So I think you already learned about discharge coefficient in fluid mechanics 1 and 2. So and then let's say we have a water level here. So the water level here is stated in this question as H equal to 2.5 meter. And the bottom one, the lower one is H equal to 0 meter. So first step that you need to do is you need to develop your Bernoulli equation. So in this question, so it is advantage for you to write a Bernoulli equation from point number 1 to point number 2 here. So and then the tricks to solve this problem by using the integration method is please do not substitute the value of H as 2.5 because the water level here is keep changing. So we assume that the Z1 here is equal to H. So I think you already know how to solve the Bernoulli equation. So we assume that the pressure here is atmospheric pressure. So the velocity at point number 1 is start from 0 velocity. And then the velocity at point number 2 should exist here. So and then the value of Z is equal to 0. So and then we could have this equation. And if we simplify the equation, we could get V2 is equal square root 2GH. So because in this question, we have discharge coefficient of 0.6, so we add the value of discharge coefficient in these final terms. So now the velocity at point number 2 can be written as CD square root 2GH. So and then we need to calculate what is the time to flow the water from level H equal 2.5 meter until H equal 1.25 meter. So the idea is simple. We use the idea of conservation of mass. So we must make sure that the flow rate for inlet must be equal to flow rate at outlet. So in this situation, we assume that the cross-sectional area here is the inlet and the flow rate at this cross-sectional area as outlet. So we could write as this one. So we have AS here, mean the cross-sectional on the surface, times the velocity, which is the dH over dt. So I already explained about this. And then at the outlet here, so we have the AP, so means the cross-sectional of pipe. So in this situation, we don't have pipe, but we have a hole. So and then the velocity is CD square root 2GH. So and then we substitute all the value here, and then finally we could have this term. So and then we could simplify the value of dH dt is equal of this one. So this is the idea. So because we want to calculate from this level to this level, from 2.5 until 1.25. So we integrate both sides. So from here, we bring the dt to the right side, and then we integrate left and right. So we will have this situation. So and then we need to put the limit. So here the limit is H1 and H2. And according to the question, it is 2.5 until 1.25. So and then if we substitute the limit in this equation, so we will get it is equal to the value of t is equal to 22.3 seconds. So means to flow water from level 2.5 until 1.525 meter, we need around 22.3 seconds. So and then another question, if we need to calculate what is the time to empty the tank. So means that to empty the tank means that we need to flow the water from level 2.5 until 0. So no need for you to do the integration process again. You just use the equation that you have. But we change the limits here. So from so the limit will become 2.5 to 0. So and then if we substitute the value, we could get the value of t is now 76.15 seconds. So mean that to empty the tank, we need to open the valve here. Okay, and then we need to wait until 76.56 meter. Here, what you need to understand is in this question, okay, we are flow out the water to become half of the tank. And then if we compare the answer, so the time is 22.3 seconds. However, time to empty the tank is 76.15 seconds. So something that you need to understand here is because of the second half here, when water flow from 1.25 until 0, the height here is lower, then the velocity that comes out here is slower. So mean that slower velocity will cause more time need to be wait until the tank was empty. So this is case number 2, which is we are dealing with non-constant tank. Okay, previously, in case number 1, we have a constant tank, means that the cross-sectional area here is constant. But now in case number 2 here, we found that our tank is a little bit shaped like this one, like a cone. So means that the cross-sectional area at this level is not same with the cross-sectional area at this level. So in this situation, you need to understand that. So the different cross-sectional area here will give you different amount of flow rate. So at the same time, the height here also give you different value of flow rate. So in this situation, we have two parameters that influence the flow rate. So we need to use these both two parameters need to be embedded in the equation to make sure that our calculation will reflect the real situation. Okay, the question is, okay, we need to calculate the time to flow out the water from level h equal 2 meter to h equal to 1 meter. So means that we need the water level is start from here. So calculate the time to flow all the water until the water level is 1.0 meter here. So first, we need to create equation. We need to know the influence of diameter with h. So what is the correlation between the h means the height of the water with the diameter? Because as I said, in this situation, the diameter is changing according to value of h. So means that we need to get the correlation. So first, we could draw a graph. As this one. So means that if we have an x-axis of h and y-axis of the water level or y-axis of diameter, According to this diagram, we could say that at H 3.0, the diameter is 1.75, and at H equal to 0, the diameter is 1. So we could draw a graph here. For H equal to 0, the diameter is 1, and at diameter H is 3, so the diameter is 1.75. So according to this diagram. So and then from this graph, I think you already know we could write an equation which is y is equal mx plus c. So and y here is actually the diameter, and then mx, so x here is h plus c. So means that we need to calculate what is the value of c and what is the value of m. And you know we have two coordinates. One is 0, 1, and another one is 3, 1.75. By using these two coordinates, you could calculate the value of m and the value of c. Okay, so finally we could write equation of this one. So mean have d of the function of h is equal to 0.25 h plus 1. Means that 1 here is the value that cross the y-axis, and 0.25 here is the value of gradient of this straight line. So we have the equation of the diameter. So in this equation, we could found that the diameter is changing if the value of h here is changed. So and then we start our calculation because we already know the correlation between the diameter and the height. So the idea is still the same. We are doing according to the conservation of mass. So we found that the flow rate must be equal, the flow rate at inlet and outlet. So we just write down flow in is equal to flow out. And the flow in here is A times V. So we have cross-sectional area, and then we have velocity, which is dh dt. So we have this one. So and then we have the flow out, means that the velocity at the outlet here. So means that we have pi dp square over 4 times vp. So p here is carries the meaning of pi. So and then we substitute the value. So and then you could simplify it. We could cancel out the value of pi over 4 here. So and then we bring the dt to the right hand side, and then the vp here we could replace with the equation that we have later on. I will show you. Okay, so we have the diameter for at the surface here. So the ds here, so we substitute with the equation of this one, and then we have dh dt. So and then we have the dp square, means the diameter for the outlet pipe, and then we have the velocity at outlet. So I think here no need for me to explain. So the flow here is square root cd to gh. So means that we calculate this by cd to gh. So and then we could do the calculation. So because we have a square here, so the power of 2, so we expand them. So and then because we have another h here, so we need to bring it to the left hand side. So now we have our equation like this one. So mean we have terms of dh in your left side. So and then we have another term of dt on your right side. So then we could integrate this term right and left, so we could get the value of this one. So and then when we do the integration, so the limit is from 2 to 1 according to the question. So and then if we substitute the value of 2 and 1, So we could find that the value of t is 234 seconds. So means that we need about 234 second time to make sure that the water level is from 2 meter to 1 meter here. So and then let's say how to calculate the volume of water after 100 seconds. So in this question, we need to calculate the volume of water after the valve is open for 100 seconds. So again, no need for us to calculate, to do the integration because we could use the equation here. Okay, so and then we take this equation. So we could write as this one. So means that we substitute the value of t equal 100 second. So and then so the limit here is, so we substitute t here is 100 second. So and then the limit here is, the upper limit is remain as 2 meter, but the second limit here is remain as h, because we need to know at what level the water will stop after 100 seconds. So that's why we could get this terms with h. So and then we could solve this problem, okay, because it is the power is quite not a common numbers, so we could solve this problem by using the Excel. So after a trial and error method, we could get that the H is equal to 1.57603 meter. So means that, so after 100 seconds, so the water level is around this height. So it is more than 1 meter. Okay, the problem is, okay, what is the volume? So the question is not about time, it is the question is about the volume of water after 100 seconds. So the H here only shows the water level. It not shows the volume of the water at the tank. So means that what we need to do is we need to use any knowledge that we have to calculate the volume. Okay, so first, because the tank is shaped like a cone like this, so let's say we extend the line here, so we have a reverse cone shape like this one. So and then this is the h equal to 0. So this is the water level according to our calculation, which is 1.57, and this is the initial level of the water, which is 2.0 meter. So and then if we draw the cone like this one, so we need to know the height from the real bottom here to this bottom. So we could get it is equal to -4 meter. So the symbol of negative shows that it is actually in a negative side in Cartesian coordinate. So means that, I think you already know we could ignore the negative because height should be in a negative value. So and then we calculate the volume of the cone. So this is the equation of the volume of the cone. So we have pi r square h over 3. And then we could calculate the value of -4 here from the equation. So let's say the diameter is 0.25 h plus 1. So if the diameter is equal to 0, so we found that the h is equal as -4 meter. So here we could understand that at this point, okay, so the diameter is equal to 0, so means that the height is -4 meter. So and then we substitute the value. So let's say we substitute here. So we know the value. So we have the 1.75 meter, and then we have the diameter of 2 here. So means that the R is equal to 1. So that's what. So the value is pi r square over h minus 3. So we have the 0.75 here. And then we have h is 6 over 3. So the value of 6 here is actually the height from 4 meter and this 2 meter. So we have I just simplified the terms. So in exam, please use the exact number there. So we have the diameter of 1.75. So so I simplified as 0.75 here. Okay, so means that the volume is 3.53475 meter cube. So you need to check the value of R here. Okay, so and then we could calculate the volume if the height is 5.57603. So we calculate the volume is 2.837 meter. So and then we need to substitute, we need to deduct this volume, because this volume is only show the volume in this area. Okay, I'm sorry, the diameter 1.75 is actually at h of 3. So the diameter for h 2 meter. So you could calculate from this equation. Okay, so mean if the h is 2 meter, so means that you will have 0.5 plus 1, so you have 1.5. So and then we divide into 2, so you will get is 0.75. So that's why in this calculation you will get 0.75. Okay, please check your calculation. So and then the value of 0.69 is the volume in this shaded area. So this is the idea to calculate the volume of water that being flow out for 100 seconds. So we go to analyze case number 3, which is the tank is not in a circular shape. So the tank is in a square in shape. So let's say we have a 1 meter length and 1 meter width of tank like this one. And then the water is filled full in this tank. So the height is 2 meter. And then as an outlet here, you will have an orifice. So we have a hole here with CD is equal 0.5 and the diameter of the hole is 0.05 meter. So the question is, what is the time to empty the tank? So we still use the same idea. Flow in is equal to the flow out. So this is the equation. So we have ASVS equal APVP. So in this situation, the cross-sectional area here is not circular, but it is in square. So we just substitute the value 1 times 1. And then the Vs here is the velocity at the inlet, means the velocity of this surface going down. So it will become dH dt. So we have a dH dt here. And then we have APVP. So this is the cross-sectional area of the orifice here. So and then this is the velocity that comes out in the orifice. So CD times square root 2GH. So I think you already know how to get this term. So and then we do the calculation. So we have dHdt like this. So and then we could integrate it, and then we could get the limit is from 2 to 0, and then we could get it is 650 second. Okay, now I will show you case number 4, which is we have a square tank and it's not and it's connected with a pipe system like this one. Okay, let's say we have a rectangular tank. So the length here is 3 meter and the width here is 2 meter. So the water level is 2 meter, and then the pipe here is 2 meter. So and then the pipe is given as this one with the Darcy friction coefficient F equals 0.05. So and then we have the K here. So the K here means the minor losses of the pipe, because I hope you still remember. So we could calculate the minor loss because we have bending here, and then we have inlet and outlet here, which consists minor losses. So we do the calculation. So we write the Bernoulli equation first to know what is the equation of the velocity that comes out from the tank. So we compare the Bernoulli equation at point number 1 and number 2. So this is point number 1 and this is point number 2. So we could get this one. So because in the question we have a lot of parameter about the losses, so we need to add a total losses in our Bernoulli equation. So the pressure is atmospheric, the velocity at 1 is 0, and the height at point number 2 is 0. So now we could have this equation. So we have the H here, we have the velocity at the outlet, and also we need to calculate the losses. So this is the equation of the losses, and this is the equation of the uh, laminar flow. The equation of major. I'm sorry, the equation of major loss, and this is the equation of minor loss. So this is major loss, and this is minor loss. So we substitute everything. So and then we could get. So we could get terms, or the equation for the V2 is 1.445 square root H. So this is a very big tips or hint for you if you want to solve this problem by using the idea of integration. Please make sure that you get equation for velocity at outlet, so velocity at point number 2. If you do not have this equation, maybe you make mistake in other calculation. So after we get velocity, outlet is equal 1.445 square root H. What we need to do is we need to fulfill the equation here. So we have the cross-sectional area, which is 2 times 3. So we have dH dt reflect the velocity of the velocity at inlet. So and then here this is the cross-sectional area of outlet, and this is the equation, or the velocity at P, mean velocity at the uh, at outlet here. So and then we could solve this. Okay, we bring the value of dt to the right hand side, and then we make integration. So we could find that the t is 3870.6 second. So bear in mind the limit of the integration is 4 to 2. So it is because if we see the diagram, we found that this is our datum. So this is our starting point. So we need to calculate the water level from this height, which is 4 meter, until this height, so which is 2 meter. Okay, so we go for the case 5. So in this case, we have this situation. So mean we have a big tank, and this big tank has outlet something like this. So the idea of having this water gate is actually discussed in fluid mechanics 1, because it is include the idea of flow in weir. So let's say we have this one. The width is 1 meter, the length here is 2 meter, and the water height is 1.5 meter. So and then this shape, okay, the bottom point here is 0.77 from 1.77 from the bottom. So the tank is 1.5 meter, but the water level here is 1 meter. Okay, we use the idea of flow rate, means flow rate at inlet is equal to the flow rate at outlet. Okay, however, okay, we have a difficulties to calculate the value of Q at inlet, because if our inlet here in this V shape, so we found that when the height here is lower and lower, so the velocity will become lower and lower. So at the same time, when water level decrease from this level to another level, so means that the area of triangle here is actually changed. So now on that situation, we need to really careful to calculate this one, and then you need to revise back how to calculate the flow rate for the triangular weir. So we call it as a triangular weir. So we already learned about the flow rate of the triangular weir in fluid mechanics 1. So it's something like this. So we assume that this is the triangular shape. So and then we need to calculate a small area first here. So we assume that the total height is h, and then the new height is small h, and the equation is b is equal to x. So b here is the distance from here to here. Okay, and then we split this one into half, because we only need these two strategy to this triangle. Okay, because if we have a triangle with a 90-degree here, it is good for us, because we could use the idea of trigonometry. So and then we could say that tangent for theta over 2 is equal to x over y. So and then we could get the total width here by multiple by 2x. So and then the x can be written as y tangent theta over 2, and then the y here, so it's actually equal to h minus h, so we write as h minus h, and tangent theta over 2. So and then the total length here is b is equal to 2x, so it is equal to 2h minus b tangent theta over 2. So and then after we know the flow rate for the small area here, okay, we could calculate the total flow rate for this triangle. Okay, so because the idea is the length here is keep changing. So means that the calculation of flow rate need to be calculated in integral manner. So this is the equation. We have a dq means the flow rate at the shaded area is equal to V times dA, and the V is given as this one. Okay, is given as this one, and the value of A, okay, I'm sorry, the value of A is actually this one, and the value of D is actually this term. So, and then we rearrange the equation because we now to integrate this one to the H, because we have a DH here. So mean another parameter is actually constant. So we integrate this one. So we have this one, and then because the integration is only for H, so we integrate here for dq, and then integration for dq here is remain as a total q, mean total flow rate at the time. So and then the integration of that one will remain this one. So and then we could found that the value is after the integral is this one. We substitute the value of the limit from h. So and then we could get this one, and then we could simplify the terms, or the equation is become here 8 over 15 square root 2g tangent theta over 2 h to the power of 5 over 2. So and then the problem is, okay, we need to integrate the value of h here. Okay, so and then we have a triangular weir like this one. So and then the height of the lowest of this peak is actually 0.77 0.77 meter. So means that the water level here is actually 0.2 meter only. So in your calculation, okay, we must know that we need to use limit from 0.23 to 0, not 1 and 0.77. So why? Because after water comes to this level, so the water will not comes out, because uh, there are no hole, or there are no area to water to flow out. So we do the calculation. So the flow rate inlet is equal to the flow rate at outlet. So flow rate at inlet is here, and flow rate at outlet is given in this equation. So what you need to understand is, it is okay for us not to calculate one by one. So mean it is okay for us not to calculate what is the area, what is the velocity. If you already have the total flow rate in this situation, we just use the equation of this one. So and then we simplify the terms, we integrate each other, we integrate both sides. So and then we substitute the limit from 0 to 0.23. So and then we could get that the time is 12.35 seconds to water to flow through the triangular weir.